Hello and welcome to this video on sketching the gradient function. The new A-level specification specifically mentions being able to sketch y equals f dash of x. If you know the function f dash of x explicitly, for example because you differentiated y equals f of x, you can use your knowledge of sketching straight line or quadratic or cubic graphs, but in other cases you won't be given the function explicitly, just the sketch. So here's an example with several features. Going from left to right, we have regions A to G. In region A, the gradient is negative, but it is increasing, which means it's getting closer to zero. The graph of f dash x is below the x-axis, but approaching zero. Note that it's not necessarily linear. In region B, there is a local minimum, and the gradient goes from negative to zero to positive. In region C, the function is increasing, so the gradient is positive. Initially, the gradient is increasing, but region C includes a point of inflection, after which the gradient is decreasing. Region D also includes a point of inflection. The gradient appears to be zero at the point of inflection, but is positive both before and after the point of inflection. Region E is similar to region C, except the gradient is not as steep, hence the value of f dash x does not reach as high. In region F, there is a local maximum. The gradient goes from positive to zero to negative. Finally, the function is decreasing in region G. The gradient is therefore negative, but as the function tends towards the horizontal asymptote, the gradient tends towards zero. Here's a worked example. Sketch the gradient function of f of x equals x squared minus 4x minus 5, showing the coordinates of any points where the curve cuts or meets the x-axis. And for our solution, well, since we have the function, we could differentiate it. But from a sketch of the curve, we know that it has an increasing negative gradient, then a local minimum, and then an increasing positive gradient. A worked example with a negative quadratic. Sketch the gradient function of f of x equals 25 plus 2x minus 3x squared, showing the coordinates of any points where the curve cuts or meets the x-axis. This is similar to the previous example, as I said, but with a negative quadratic. We can complete the square to locate the local maximum. The gradient is decreasing throughout with a value of 0 at the turning point. This time we have a cubic. Sketch the gradient function of f of x equals 1/3 of x cubed minus 4x squared plus 12x minus 1, showing the coordinates of any points where the curve cuts or meets the x-axis. Well, this gradient function has just been determined by differentiation, and it's quadratic. A worked example from the textbook. The diagram shows the curve with equation y equals f of x. The curve has stationary points at -1, 4 and 3, 0, and cuts the x-axis at -3, 0. Sketch the gradient function y equals f dash of x, showing the coordinates of any points where the curve cuts or meets the x-axis. Well, this time we do not have the original function, so we have to use the diagram. When x is less than -1, the gradient is positive and increasing. The gradient is 0 at the maximum point. Between -1 and 1, the gradient is negative, decreasing before the point of inflection, then increasing afterwards. There is then a minimum point, after which the gradient is positive and increasing. And here we have the answer. The original function looks a bit like a cubic, so unsurprisingly, the gradient function looks like a quadratic. The second worked example from the textbook. The diagram shows the curve with equation y equals f of x. The curve has an asymptote at y equals -2 and a turning point at -3, -8. It cuts the x-axis at -10, 0. Sketch the graph of the gradient function y equals f dash x, showing the coordinates of any points where the curve cuts or meets the x-axis, and state the equation of the asymptote of y equals f dash x. Solution. Well, again, we do not have the original function, so we have to use the diagram. When x is less than -3, the gradient is negative and increasing. The gradient is 0 at the local minimum at x equals -3, and when x is greater than -3, the gradient is positive and increasing until the point of inflection. Then it decreases as the original function tends towards the horizontal asymptote and the gradient tends to the x-axis. So the answer is shown in the graph, and the asymptote of y equals f dash x is the x-axis, or y equals 0. One final worked example. The diagram shows the curve with equation y equals f of x. The curve has asymptotes at x equals -3 and x equals 5, and a turning point when x is 1. Sketch the gradient function y equals f dash of x. Solution. When x is less than -3, the function tends towards the x-axis. As the function approaches the vertical asymptote at x equals -3, the gradient is positive and increasing. There is no gradient at x equals -3, so we have an asymptote there as well as for the gradient function. Between -3 and 5, we have a decreasing positive gradient, a local maximum at x equals 1, and then a decreasing negative gradient. Just like when x was -3, there is no gradient at x equals 5, so we have another asymptote. And finally, when x is greater than 5, the function once again tends towards the x-axis. The gradient is negative and increasing, tending towards the x-axis. And finally, here is the answer shown in the graph. Thank you very much.